So now to continue with this idea of proportions, let's look at what we call direct proportionality and inverse proportionality. And then there's something that's called joint proportionality, but that's really an extension of direct proportionality. First, if we say that A is directly proportional to B, that means that we can write the equation A equals KB for some constant K. Could be a positive number, could be a negative number, could be a big number, could be a fraction, but it's some constant K. All right. Inverse proportionality is like this. A is inversely proportional to B. It means that A equals K times 1 over B, or similarly, A equals K over B. So graphically, it would look like this, right? A directly proportional relationship is simply a line where K, that constant, is the slope of that line, right? So here we have a graph of Y being directly proportional to X, right? And that there are infinitely many such relationships depending on your value of K, the slope, right? Y is inversely proportional to X looks like this, that characteristic 1 over X shape. All right. I need to continue into the negative, but it would be simply the mirror image in this quadrant, and of course the direct proportionality would go in a straight line. So for example, we could say that the heat added to a system is directly proportional to the temperature of the system, as long as you don't reach a phase change, the water doesn't boil or what have you. So Q, if you remember from chemistry, is often used for heat added or taken away, and we can say that's directly proportional to temperature. An example of inverse proportionality would be if, say, you have a certain distance you need to cover, therefore that distance remains constant. Your speed is inversely proportional to the time it takes you to get there. All right. So what does that mean? If two values are directly proportional to each other, that means, so as you know, A is directly proportional to B, that means that as B increases, A increases. And if A increases, B increases. No problem. And similarly, if two numbers are inversely proportional to each other, then that means as C increases, B decreases. And if B increases, C decreases. All right. Numbers can also be proportional to some function of another variable. For instance, we could say A is directly proportional to B squared. Okay, where B squared is thought of as a unit, and A varies proportionately to that B squared. You can also have AB proportional to the square root of B. All right. You can also have the same sort of thing happen with the inverse relationships. For instance, I could have C vary inversely as square root of D, or C vary inversely as D to the fourth. All right, so here are a couple examples. Write equations for the following relationships. A is directly proportional to C. So part A here will have A equal to KC for some constant K. B, L is inversely proportional to H. Now, it's a separate problem, so you can use K again, even though it would be a different constant of proportionality. Some people like to change up the letter and use a different letter besides K. That's all right, we'll leave this alone. Next, let's consider this sort of problem where you have to find what that constant of proportionality is. And generally speaking, that means you're going to have to get at least one scenario, that is to say one set of the values of the variable, right? So if d is directly proportional to z and d equals 12 when z equals 3, what is the constant proportionality? Well, let's start with writing ourselves an equation. So d is directly proportional to z. Okay, and then to find what k is, to find what that constant of proportionality is, we simply substitute our two values, or values for the variables, and solve for k. All right. So 12 equals k times 3, and we simply divide by 3, and get the k equals 4. Alright, so the next kind of problem we can run into will ask you not just to find that constant of proportionality, but to rebuild your original equation and then apply it, right? It's give you one of the values and you have to find the other, alright? So here, for example, if w is inversely proportional to y, and when y equals 10, if w equals 10, y equals 1, what will w be if y equals 2? Right, so the first step is to write ourselves an equation. So we'll start with w equals some constant over y. Then we'll substitute in our 10 for w and 1 for y so we can find out what k is. And then solve for k. Well, k over 1 is k, so 10 equals k. All right. Now, in order to complete the rest of the question, we're going to have to put that back into the original equation and then evaluate the equation with y equals 2. There's our full proportionality equation with the constant already determined. And now let's find what w will be when y equals 2. And there we have it. And here are a couple for you to try. If x is directly proportional to y and x equals 4 when y equals a half, what is the constant of proportionality? And t is inversely proportional to z. What is t when z equals 14 if when z equals 7, t equals 2? Here's a chance to pause quickly, give it a try, and then come back and see how you did. And let's see how it went. If x is directly proportional to y, okay, we'll stop there for a second and write ourselves our direct proportionality equation. X is directly proportional to y would give us x equals k y, and then we can use the values given there in this equation to find what k is, right? So when x equals 4, y equals 1/2. Multiply both sides by 2, the reciprocal of 1/2. You could also divide by 1/2, same thing, times 2, k equals 8. All right, how about this one? T is inversely proportional to z. What is t when z equals 14 if we have this situation, right? So they give us one specific example. All right, so first off, let's get ourselves our equation. T equals k over z. And they give us one specific scenario here, right? So we have a value for t and a value for z, and that allows us to find k. So we'll put 2 in for t and 7 in for k, for z, and get our value for k. I'm going to multiply both sides by 7 to solve for k, and we get k equals 14. And a final note, things can be what's called jointly proportional, all right? And you can have things that carry multiple proportionalities, okay? So for instance, A is jointly proportional to x and y, means that it's proportional to both of them, so to speak, and it looks like this. right? And if you were to have a problem that asked you to find the constant of proportionality, you would have to have an instance of all three, right? You have to have the corresponding values for the three of them at some point to get that value. You can also have things teamed up, so we could have something like A is directly proportional to and at the same time inversely proportional to B. So what would that look like? That would be A equals K B for that direct proportionality and over Z for that inverse proportionality. Okay? So, I mean, theoretically, of course, you could take a different K for each one, but then, of course, you would end up with one constant as the product or amalgamation of all of those constants. So it's okay to write the whole thing with just one constant from the get-go. And I can't be a good physicist and lead the topic of these different kinds of proportionalities without at least mentioning one of the greats among these kinds of equations. And here we have Isaac Newton's inverse square law, that the force of gravity is jointly proportional to the masses of the two objects that are pulling on each other gravitationally. We'll use the big letter G here for the constant that we use for this equation. It's something that's measured and tabulated and, as far as we can tell, uniform throughout the universe. And so it's jointly proportional to those. We will often use, say, a little m for the little object sitting on top of the planet and the big M for the mass of the planet, but that's somewhat loose. But inversely proportional to the square of the distance between those objects. And since we're often talking about planets and things, distance from the center of the planet is nicely measured as a radius, so we use r. There we have it.